Hello, everybody. Today, I'd like to present our paper on facial landmark predictions with applications to Metaverse. My name is Han Qiao. I am a PhD student at Nanyang Technological University in Singapore. A bit background about myself. I graduated with a master's in engineering in computing from Imperial College London. I am currently also working as a software engineer at Supabase, where I build open source tools for the Postgres ecosystem. The best way to motivate our paper is perhaps to show you how animations are made in the film industry today. So here we can see that on every actor's face, we strap on a very expensive motion capture rig that with a camera pointing at the actor's face. And there are many white dots painted on the actor's face at key positions. So these white dots are what we call facial landmarks. By knowing the movements in these facial landmarks in 3D coordinates, we will be able to apply them to any 3D models to animate them, such as in this case, the model of an ape. And this technique is used widely in many films because the result is just amazing. It can produce very natural looking animations without having a dedicated animator to help with it. But the problem is also quite obvious. So one issue is that these rigs are quite expensive. You need to hire actors and also buy those equipment. We are looking for ways to perhaps replace or improve upon this setup. The second use case we have is, of course, to make the avatars for Metaverse more natural looking. Now, avatars are key ingredients of the Metaverse. They are your identity that you bring to different Metaverse experiences. And one idea here is to see if we can use machine learning algorithm by studying from videos in the wild to learn what are the natural human expressions. This form of learning will be more free from biases introduced by human animators. And last but not least, we can also try to improve accessibility of Metaverse content. Imagine if you are deaf or mute, the predominant approach today was to drive these facial expressions using your voice, right? So we would also like to try to use text as the input so that even if you are deaf or mute, you can use the keyboard just like you type on the internet today. So this will bring more diversity to the Metaverse experience. The related works in this academia is mostly divided into two branches. The audio-driven approach uses audio waveforms like Mel spectrogram to predict facial landmark positions. These are called the active shape models. When applied to Metaverse, these techniques have a disadvantage that we need to first translate text to audio and then from audio to sequence of images. And the other approach is to use text-driven models. So this will take text directly as input, but most of the existing techniques requires hand-drawn animations. So the model will only predict a set of parameters that is input to these hand-drawn animation models. So of course, the downside is this is a more constrained way of animating your face. So our approach, we really try to go directly from text to the free-form landmark positions in 3D. And it is worth noting that this is the reverse problem of lip reading, where given a sequence of images, you're just trying to decipher what the words were spoken by this person. So actually, we have, because of this similarity, we can reuse some of the data set that was trained for lip reading. This area also gained a lot of industry attention from companies like Meta and NVIDIA. Meta has released the audio-visual Hilbert model that works on lip reading 3 sentences with very low error rate using just 30 hours of video footage as training data. This demonstrates that few shot training is effective in this use case. Meta also has the Quest Pro device that has a built-in face and eye tracking hardware. So this allows them to gather even more training data by capturing both your voice to the microphone as well as your facial expressions to hardware sensors. NVIDIA took a slightly different direction. It focused more on the animators. So using the audio to face program, you can turn some knobs to adjust the emotions of the generated speaker. And this is a photorealistic rendering of the speaker. Very impressive. In the open source community, we have also a few tools that help animators generate lip sync videos from either voice or text. Now, as mentioned, our approach uses the keyboard or text input directly, and we pass that through a machine learning model, which outputs the lip key points in 3D coordinates. And then we pass these coordinates to a 3D engine, which finally animates the avatars for us. A lot of these components have been figured out by existing tools, and our job is really to focus on the machine learning model so that we can output more realistic or more natural looking lip movements. So to train such a model, there are two essential ingredients. First of all, we need the transcript, the audio transcript as the text input. This is quite readily available from the automated captioning tool on YouTube videos. The second ingredient is a bit difficult to obtain, and that is the ground truth labels of the speaker. So we obtain these ground truth labels not with motion capture rig, but by applying another machine learning model called the OpenFace 2.0 model on raw footages of public speakers. So as shown in the example here, the OpenFace 2.0 model predicts the landmarks around your lips, around your eyes, and it also outputs the pose of the head, which direction is pointing. And using these two as input and output pairs, we can regress then on the L1 loss between the predicted landmark position and the ground truth landmark positions. Now, now you may ask, like, how do we translate language to a sequence of animations? Actually, there's a very similar approach by those two different models. So in the NLP world, we will encode a piece of text into token embeddings. And the task is really to predict the next token based on the context of what the tokens the model has seen before. And in the landmark, facial landmark prediction, we are also thinking in similar lines. We have a sequence of frames that happened before, and we want to predict the next frame that is going to happen, where your mouth is going to move next. So these are two actually very similar problems. The data set we use, first of all, primarily is the lip reading sentences 3. These are composed of TED Talk videos clipped to about 3 seconds in length, where each clip is focused on just the speaker's front profile. So this gives very good data for our OpenFace model to extract landmark from. The OpenFace model runs on these videos to generate training labels. There are some inaccurate cases that we have removed by manual filtering. The last data set we use is the LJ Speech 1.1 dataset, which is widely used in the text-to-speech synthesis task. And the idea here is that we want to borrow some of the embeddings of the parameters, trained parameters of the encoder, which essentially you can think of it as distance vectors between the similar words and the different words. So the idea is that if two words sound similar, they are probably produced by similar mouth movements. The way we generate labels, like mentioned, is a rather elaborate process. First of all, we realize that the OpenFace 2.0 model only works on some videos, and those are higher resolution videos. So we remove all those that are 480p or less. And then we also identify clips with minimal camera movement. So we can accommodate slight movements in the head of the speaker, but if it's moving a lot, changing different angles, then the open face model kind of breaks down. So in this example, on the first row, on the top row, we have the misaligned model. You can see the landmark positions are pretty much not on the speaker's face. But on the bottom row, we have almost perfectly aligned landmark positions. You can see the eyebrows and the lips are clearly annotated. We also get the rectangular box to represent the rotation and the translation matrices of the speaker's head. And using these matrices, we can reproject the speaker's head in 2D back into 3D. And this allows us to normalize the speaker's front profile to obtain a reference set. And this is very important because when you are asking a model to predict the movement in the lips, you are actually asking the model to predict displacement from a reference position. If we just take the raw 3D coordinates, the model is going to learn the absolute position, and it's not going to give you good results, right? So the model we used is a modified version of Tacotron 2. The blue segments are encoder layers, and the green segments are the decoder layers. The gray segments are the components we have removed from the original model, because in our experiments, we found that using those layers did not actually contribute to better predictions for our landmark prediction task. And we have also reused the encoder layer weights as well as the gate layer weights for two reasons. One, the encoder layer weights, as mentioned, has captures the distance, how similar and how different words are. So those can be reused because they have been pre-trained on a much larger speech data set. And the gate layer weights determines when the next sentences stop. This is very this does not change whether you are trying to predict, whether you are trying to generate landmark trajectories or generate Mel spectrogram. Therefore, we do not have to touch this layer. Using these simplifications, we are actually able to kick off our training using just 80 clips of videos, which equals to about 5 minutes in length. We ran about 5,000 iterations at a batch size of 8 frames per batch. So the L1 loss we achieved at the end of the 458th epoch is 0.0075, which shows convergence. And we also use the 1,000 max decoder steps, where 80 steps, where each step can be roughly equivalent to 1 frame in a video. So at 80 frames per second, we can generate for 12.5 seconds of a full-length animation sequence. We also use the Adam optimizer with a few other optimizations that you can find the exact configuration parameter in our paper. And finally, we can show you some of the evaluation videos that we have generated from the model. On the left, we have the predicted landmark position, and on the right, we have the ground truth landmark positions. Now, if you can look closely, both pronunciations, both models, both pronunciations are tried to say the sentence "It's not just my work," and you can see the predict and the ground truth quite closely resemble each other. Now at inference time, this is where we can apply this technique more widely to the metaverse. We can, given an unseen piece of text, we're able to generate lip movements for those. So here, we're trying to get the model to say, "Hello, world." It's a short clip. So if you need to rewind, please go ahead. The way we generated this animation at inference time, it's not as straightforward, right? Because the model predicts just the displacement. So we need to add on to it the reference landmark positions and then render the final frame. And this also gives us the opportunity to customize the model based on different speaker profiles. If you have a wider lips, for example, the displacement probably wouldn't change much, and we can just displace the lip positions on a different speaker profile. And lastly, there are some limitations of this paper. First of all, I think it's very difficult to evaluate fairly lip movement because this is a multimodal problem. If someone is doing a public speech versus someone is whispering to your ears, their lip moves are probably going to be very different. Similarly, if you have angry emotion versus a cheerful emotion, the way you speak are probably going to be different. And of course, this does not account for accent as well. So the second thing to note is that our model is constrained to lip displacements only at the moment. We tried to generate for the whole face. However, the result was not very good due to the lack of data. And last but not least, the training of these models is kind of expensive. We used 800 GPU to train for 7 hours if using just 5 minutes of data. If we were to look at deploying such devices on Oculus Quest or other edge devices that is low on power and lower compute, we probably need to do some further optimizations. So to conclude, we have proposed a weakly supervised approach to generate visual landmark positions directly from text. And the labels are generated fully automatically using old videos in the wild. We have applied transfer learning effectively from text to speech encoder states. And we are also able to train using just 5 minutes of video footage. The trained model is customizable to each speaker's individual profile, and it does not require any domain expertise in acoustic or linguistic features, as the model is trained fully end-to-end. You can find our code on GitHub, and we'd like to thank you for your attention and open the floor up for question and answer.